Hi, here we present our work, Adaptive Prototype Learning and Allocation for Feature Segmentation. What is feature segmentation task? Basically, given support pairs, which are support images and object annotations, we expect the design model can find the same object in the query image. We observe some drawbacks of the current methods that use single prototype learning. Firstly, merely one prototype is used to represent all the object information, which can lead to ambiguities. Second, the prototype delivers equal guidance to the query feature, which makes the guidance less discriminating. Motivated by that, we leverage feature clustering to generate the adaptive number of prototypes. Then, we allocate the most matched one to each query feature element. We expect the prototype to be adaptive to the object scale and valuation. For example, large object carries more information, and thus should be represented by multiple prototypes. While background takes up a large amount, single prototype is sufficient for foreground object. We conduct first feature-based superpixel extraction on the support image, and the resulting superpixel central edges are considered as prototypic features. Then, we allocate the central edge pixel-wisely to the query feature based on the cosine similarity. We introduce two modules, superpixel guided clustering and guided prototype allocation, and build the ASG.NET. This is a typical two-branch structure. We first input support and query images into a shared convolutional neural networks to extract feature maps. Then, we implement feature-based clustering inside the support mask to extract superpixel central edges. With this central edge, we leverage GPA module to achieve pixel-wise guidance for query feature. Finally, the fused feature is sent to a FPN-like structure for multi-scale fusion. In SGC module, we first append spatial information to the support feature, and then we conduct differentiable clustering within the support mask area to extract superpixel central edges. In GPA module, we first compute the cosine similarity between each central edge and the query feature to get similarity maps. Then, we achieve the information guidance in two branches. In the first branch, we get the index of central edge with the high similarity for each query feature element, and we insert the corresponding central edge to set up a guide feature. In the other branch, we simply sum up the similarity values along the first axis, which can acquire a coarse segmentation map. Finally, we concatenate these two outputs with query feature and thus obtain the merged feature. Notice that we set a criterion to adaptively choose the number of prototypes based on object scale, so large-scale objects will be represented by more prototypes. While when heavy occlusion exists in query sample, our method can select the most relevant prototype to deliver matched guidance. Here we show some quantitative comparison. On Pascal VLC dataset, we exceed the state-of-the-art 5-shot result by 2.4%. While on COCO dataset, we exceed the state-of-the-art result by around 5% in 5-shot. Here we show some qualitative examples. We take the single prototype learning as the baseline for comparison. As shown in the results, our methods perform particularly better in occluded cases. We show the visualization of similarity maps, which are the cosine distance between prototypes and query feature. We found that each map represents the partial information of the object. Note that the number of similarity maps is determined by the size of support object. Thanks for watching. For more details, please check our project website.